In this video, we're going to look at approximating a cosine value using a Taylor polynomial. So we're asked to find the Taylor series centered at x equal to pi over 6 for the function f of x equals cosine of 3x, and then we're asked to use this series to approximate cosine of 3 over 2 to within 1/100,000th. Actually, I guess that's a 1/1,000,000th. Anyway, it doesn't matter what this decimal is, we're just going to use it for our remainder form. Okay, so the first thing we do, of course, is we take a whole bunch of derivatives and look for a pattern. So derivative, if f of x is equal to cosine of 3x, the derivative is negative 3 sine of 3x. Second derivative is negative 9 cosine of 3x. Third derivative is a positive 27 sine of 3x. Fourth derivative is a positive 81 cosine of 3x. What we're noticing here is that we have odd powers of 3 that are going to end up surviving. Notice that when we plug in pi over 6 into f, we get 0. We also get 0 when we plug it into the second derivative, and when we plug in the fourth derivative, and any even derivative we get, we're going to end up with a cosine. So when we plug in pi over 6, we're going to get 0. For the odd derivatives, notice that we get a 3 to the first, a 3 cubed. The next one would be a 243 or a 3 to the fifth. So we're getting the odd powers of 3, and then they alternate, starting with negative, and then positive, and then negative. Okay, so we notice that again that the odd derivatives are the only ones that are non-zero. We'll index that with a 2n plus 1, as n goes 0, 1, 2, 3, and so on. So the nth derivative, the 2n plus first derivative of pi over 6 will be negative 1 to some power. We said we started off negative. So when n is 0, we want to get a negative 1, which means I need to do an n plus 1, or an n minus 1 would also do the trick, either or. But the reason why we're doing n plus 1 is because the first one is negative, and then the 3 to the 2n plus 1, because we've already observed that these are the odd powers of 3 that we're getting. All right, so again, we're indexing everything with odd derivatives because the even ones are all 0. So when we do our Taylor series centered at pi over 6, if we index from 0 to infinity, the only terms are going to be the odd ones. So we're going to get the negative 1 to the n plus 1, 3 to the 2n plus 1 for our derivative form. Then we're going to get a 2n plus 1 factorial in the denominator, and an x minus pi over 6 to the 2n plus 1 as well. Because again, it's only the odd terms that are non-zero. Well, we notice, in order to get an approximation of cosine of 3 pi over 2, we can plug in 1/2 for x, and that'll give us cosine of 3 pi over 2 on this side. So plugging in a half into the series gives us this expression. Just again replacing the x with 1/2. This should be a 1/2, not a 3/2. This 3 should be a 1 here. It's correct the rest of the way down, but that should be a 1, not a 3. That's a typo. My apologies. But again, we're just replacing the x with 1/2 here. Everything else is staying the same in the series. We want to use the Taylor form of the remainder to get a bound on the remainder. So the Taylor form of the remainder, the numerator, involves bounding the n plus first derivative. Well, every time we take a derivative, we're going to get a sine or a cosine piece. That piece is always less than or equal to 1. And the coefficients out in front were powers of 3. Notice that the original function had a 1, the first derivative had a 3 to the first, second derivative had a 3 squared, third derivative had a 3 cubed, and so on down the line. So the n plus first derivative is bounded in absolute value by 3 to the n plus 1, no matter what the x is. So if we use the Taylor form of the remainder for a value of x has to be less than or equal to the bound that we just found on the original remainder, or excuse me, on the original derivatives here, over n plus 1 factorial times x minus pi over 6 to the n plus 1. And this is true for all x because we know that the bound on the n plus first derivative is given to us by 3 to the n plus 1, no matter what x is. So now we substitute 1/2 into here because we're interested in approximating the series when we plug in x equal to 1/2. So this is the expression we get. And if we guarantee that this is less than 1/1,000th, then we guarantee the remainder is less than 1/1,000th. So we're going to look at this inequality looking at this Taylor form of the remainder being less than a millionth, there's no really good way to solve this for n, so we're just going to do this by brute force. If you plug in n equal to 3, we get something close to what we want, but not quite. It's a little bit too big. When we put in n equal to 4, we're finally less than that bound. Well, if n is equal to 4, that stands for the degree of polynomial we want to use. So we want to use a fourth degree polynomial to approximate cosine of 3 pi over 2. Of course, in the power series for the cosine of 3 pi over 2, the fourth degree term is 0. So we'll only need the first term, what we get when we plug in n equal to 0, or that first degree term there, and the third degree term, what we get when we plug in n equals 1. Remember, these n's here, it's a little confusing. These n's here are the degree on the polynomial you need to use. It's not the same as the index here in this case, because we used n here, but the indexes are always odd. Again, we use a fourth degree polynomial because this turned out to be 4 to get a remainder small enough, this part here. So I would write out my series till I get to the fourth degree term, but my fourth degree term is 0. The only terms that we have in this case are odd ones.